So, so welcome you all in this diagnostic plot. So diagnostic plot is really important for understanding the features inside our reservoir. So analyzing the pressure response of well to determine information about the reservoir. So whenever we discuss a diagnostic plot, actually we have two graphs simultaneously plotted in a log-log plot, so that we have the pressure versus time, as well as we have the derivative of that pressure and the time. So each and every segment having a specific characteristics in specifically in the diagnostic plot, so that we could understand what is the nature of the reservoir or how the flow is occurring. Okay, so this is very important in terms of analyzing the complicated structure of the reservoir. So I just take 1 minute within the slides. We have already discussed. So as we start taking our production, or maybe we start our well test acquiring well test data through our electronic memory gauge. So what is there? Your pressure pulses will move away from your well bore, and it will go in different segments of your reservoir, and then it will reach the boundary. So what is happening in time? Actually, the storativity and transmissivity of a specific compressible zone will be reflected in the pressure behavior, and then by using different methods, actually semi-log plot, log-log plot, normal pressures versus time plot, we try to understand how actually the pressure response is, and actually what is the surrounding of the reservoir, what are the environment of the reservoir in that specific region. So by using that, we try to understand so many important parameters about the reservoir. Okay, so if you just see this, we have discussed in the last class in different state line domains. State line domains mean depending on the slope. We have earlier discussed. So this is specifically the well bore storage effect having a slope 1. Then we are getting a spherical flow where you have a negative half slope. Then we are getting a homogeneous reservoir where the derivative slope is 0. That means we are having more or less constant supply of material to support our flow. And then we are getting again the pseudo steady line. Even this part, each and every part, we try to understand today with a different diagram and different perspective. So simultaneously, we'll try to see the conventional plot as well as the diagnostic plot, so that we'll understand what is happening. So these are the different flow regimes we have discussed earlier. Well bore storage, then you may have a radial flow, you may have a bilinear flow, you may have a linear flow, elliptical flow, spherical flow, pseudo steady flow, and constant pressure boundary. So each and every type of flow actually dictate a pressure response, and that is giving us information regarding the reservoir surrounding, or maybe the flow through which the reservoir reservoir is now flowing through, okay, or going through. So this is what the flow regimes are. Then if I just give you the formulations, this is in Cartesian plot, and this is in your cylinder radial diffusivity equations. Okay, so we have seen the solution of the diffusivity equation. Okay, earlier. Here the relations between our dimensionless values, dimensionless pressure with normal pressure, field pressure, dimensionless time with the field time, measured time, then you have radius, dimensionless radius with your relations between radius of the reservoir or study radius and the well bore radius. This is half distance. The dimensionless, your fracture length. Okay, it is fracture length. Okay, and this is your well bore storage formulations with respect to the C. Okay, so these are and how you solve it. We have discussed this a Cartesian and in the dimensionless form. Okay, diffusivity equation. And this part also we have discussed, depending on the type of your type of your, or maybe your X value. That means your the X means the relations between time and the radius, we convert into X by changing Laplace transformation, and then using our line source equations, we have solved the equations in different form. When you have specifically the X value less than 0.01, we discussed we can take the logarithmic approximation for measuring our pressure. If pressure or X value is more than 10, we could use them, because the pressure will not change there, it will consider to be initial pressure. And if the value of the x specifically in between 0.01 and 10 or maybe 3, that time we have to really consider the exponential integral expansion and calculate our value for the specific pressure solution. Okay, so that we have discussed earlier. We discussed this part also. So if you see, we have a normal pressure value with specific parameters of CD e to the power 2s, where you have a Wilbur storage effect and the skin is involved. And we discussed in our type curve also. So when you have this value 1, that means it is going to be a normal well having no Wilbur storage, no skin here. If the above part, these are the damage well. If you are going below, these are the generally your stimulated well. Okay, so that in case of normal. And if you remember, I discussed one dotted line in our derivative plot. So that means in normal pressure graph, you may not understand where the infinitely acting domain start. But once you do the derivative, so you can understand this part is considered to be, one slope is considered to be Wilbur storage effect. Then this part is considered to be the skin part is affecting. So this is your spherical flow minus slope. Then again it is coming to slope 0. Okay, derivative is coming slow. That means we are in the infinitely acting domain. So that we have discussed. And again, after the infinitely acting domain, the graph may change depending on the support system in the boundary. Okay, so this part we have discussed. So now you see in the Wilbur storage effect, we discussed earlier, steady state everywhere. If you see, always there is a relations. We try to manage the plot in an y equal to mxc form. So whenever we discuss in the last class also, so depending on that, we got here half slope. Okay, half slope means the power of the is TD, power is half. Here related to T power is 1/4 in bilinear case. Then if we see the sustained elliptical flow that we haven't discussed in the last class, sustained elliptical flow, if it is there, then the power would be 3/8. So that means each and everywhere, depending on your slope, you could understand what type of flow is occurring inside your reservoir. Boundary influence elliptical flow, this would be also 2/3. Okay, so that means you see we are trying to plot pressure versus your specific time in a derivative plot. Okay. So now these are just slopes, flow regime. So how do you identify flow regime? Just to identify the slope of the graph where you are plotting. We have discussed in the last class also linear flow. We have the half slope, then we have the 1/4 slope. Okay, pseudo steady flow 1 slope, then sustained elliptical flow 3/8, boundary influence elliptical flow 2/3, and then you have a radial flow no slope. Okay, radial flow means infinitely acting domain. So depending on the flow pattern, we could understand that flow behavior. Okay, so this part up to this more or less we have clear our understanding. So now I'll go one by one what is happening. So this is a radial flow. Let's say if when we are discussing the radial flow, you see it is coming from all directions. But when you have a boundary or maybe a fault which is a no supply fault, then you can see your supply is not from throughout the whole 2 pi r. Okay. So that is how because we are discussing the pressure response is very much related to the flow behavior, flow. If the flow is following the same value, that means your pressure will be sustained and it will give you a constant value. But if the flow is not that much, due to maybe whatever may be the reason, we may not get the same response in our pressure behavior. And now from our point of view, we need to analyze what is the actual situation, why the flow is not sufficient. Is it due to the normal restriction or due to some features, geological features which is restricting our flow so that we are not getting properly the flow. Okay, so this is what the important part is. What is there? That means we may have restriction, we may have some other geological features which is restricting our flow. That means ultimately we are not getting proper Q to sustain or to maintain that specific pressure at the well bore, because that is now the recording going on continuously when the flow is occurring or we are allowing a well to flow or maybe close. Okay, so that means pressure pulse is moving away from your well. Okay, so now if you see what is the philosophy behind it. So if you see here, initially we have a slope. Initial part, if we consider this early time, it is a slope M. Okay, that means a specific flow pattern is occurring and we are getting a straight line area. But once you are not getting sufficient amount, your slope will change. That means the value of storativity and transmissivity, that means the geological feature due to which the flow is not supported equally for the production we are taking at a specific rate into our wellhead. So that's why what is happening, if you saw initial up to that time, you are getting a flow of M1. Okay, then what is happening, your slope has changed because you are now getting a restriction. Okay, so that's why we are not getting the proper flow there. Okay, so what in semi-log graph we will be having this type of. Okay, so now once you see a semi-log straight line characterize the log plot PD versus this time, that there is a derivative plot, so you can understand. You could understand particularly the derivative plot, what is happening. So once the semi-log straight line characterized on the log plot, so what here you are having a log plot or semi-log plot, but here you are getting a log plot in the diagnostic plot where we have this stabilization of the derivative at 0.5. So you see when there is a change in your flow pattern, you get a stabilization. That means what, after you have an average. Initially what it was a 0 point is 0 and you are getting, but when you have some restriction of flow, you will be getting at 0.5 stabilization. Okay, so whenever you are plotting a log plot, you got a value here at 0.5. Okay, so now, so this is, so the doubling of the slope characteristic in the fault is characterized on the derivative by doubling in the level of derivative. So you can understand here, so it was 1 in case of normal infinitely reacting domain, but if you have a fault, okay, fault or maybe some restriction in flow, that time, that means you are getting a 0.5 stabilization. So this is due to the fault movement. Okay, so that means what is happening, so initially you have not yet reached the infinite latent domain. Before that you will encounter a fault, and for that your flow behavior will change and you are getting a stabilization of your 0 slope at 0.5 units. So 0.5 means in this log. So when the time, you see the time when the derivative leaves, the first stabilization can be used to determine the radius of investigation of the test corresponding to the time when the compressible zone reached the fault. So you could now understand when, that means when we are reaching a specific stabilization, the radius of investigation formulation you could use to understand where the fault is, how far from your well the fault is. Okay, so determination in this way is more accurate than the result obtained by the conventional method. So you could understand the philosophy behind distance measurement with the help of your derivative plot. Okay, so this is what we are trying to understand by plotting our derivative plot. Okay, so now when you have a channel, you see the slope of the graphs are changing depending on the supply of the material. So channel should be understood in terms of the fluid mechanics. It does not necessarily correspond to the geological acceptation. That means channel means it may not be a geological features. It may be somehow the things of the flow behavior has changed. So dynamic channel can be due to number of causes such as two parallel sealing faults. Okay, so what you are encountering, a well which is in between, and you are getting the faults which are no flow boundary, a sedimentary deposit channel. So you may have a channel which are sedimentary rocks with porosity and permeability where you have your well, but these two layers are not related to your flow, or they are not supporting anything. So two parallel lateral variations in phases. Okay, so that means physically they are different in nature and they are not supporting to your flow here in the well. So the channel is defined by its width L and by the distance D from the well to one of its edge. So now you see you have a two sealing fault, you can say, or you can say the permeability barrier where you are not permeability barrier, it's a completely closed permeability or no support is there. So during a well test inside a channel, several flows follow one another. So I told you earlier, you may encounter different, this is very important. I'll just read one by one, and you have to understand how the slope of the graph will change when when the flow encounters, so that you can say the compressible zone reach from one zone to another zone, or maybe the system. Okay, radial flow until a no flow boundary has been reached. Okay, so you can understand the flow exhibit the usual infinite reservoir behavior, a semi-log straight line, and stabilization of the derivative at 0.5 if the Volvo storage effect ended soon enough. Okay, so this is first 0.5 I told you if it is encountered. First stage of the channel. Fault effect, when the compressible zone reaches the nearest channel is, the boundary has exactly the same effect as a ceiling fault, what I discussed, in an infinite reservoir. The slope of the semi-log straight line doubles, with the derivative going for a stabilization at 0.5 to a stabilization at 1. So that means when you encounter the first fault, which is very near to your well, so you will encounter the first stabilization of your infinitely acting domain, you can say 0.5. Then again, once you go ahead, you may stabilize at 1. Okay. So this is observed when, if the well is very much off-centered in the channel, otherwise the two edges are reached at the same time and no fault effect is observed. So that means if you are getting a channel means you are having some sort of restriction or things. Okay, so that time, depending on your locations of the well, from the two end of the channel, you may get different types of flow. I'll come after that. Okay, the channel, when the compressible zone reaches the two edge of the channel, it expands linearly parallel to the edge of the channel. So it will move both directions as the flow is supported. Okay, so that means what, if I just go, you can understand now in the three situations. Okay, so it's a bounded channel. Okay, bounded channel means, in, you see the first case, it's one where you don't have the boundary. Here you have the boundary, which one boundary is very close, where the boundary is far away. So now what is happening, initially you were getting a stabilization here. Okay, one, you see this is more or less one part. Okay, so now as no flow boundary at one end of the channel is perceived by doubling the slope of the semi square root straight line, that means we discussed it is. Okay, now on the log-log plot, it corresponded, so this is a conventional plot. Okay, so now in case of log-log plot, it corresponds to a pressure derivative going from an initial 0.5 slope straight line to a second 0.5 slope straight line. Okay, that means initially you have encountered a fault sort of thing, then again you are moving out 0.5. The doubling of the slope on the conventional plot corresponds to the transition of the second straight line by 2 on the log-log plot. Okay, so this is what is happening. So it's coming to 1. Then you see this graph, and this graph, they are just shifting depending when it is encountering. So in this case, you see it is encountering initially both the sides, then the flow is occurring in both the sides. In this case, you see here you have very close boundary. So again, the flow is not sufficient. That's why the slope of the graph is very fast, because it touches here early. Okay, then in this case it has touched here, up to this is same, but in this case this boundary has touched earlier, so the slope has been increased. That means the flow from this direction is not there. In this case it is slightly away from it, that's why it started from here going up. That means flow is not sufficient, limited flow. And in this case, in the third case, you can see the flow is in both the sides, so your slope is still less. Okay, so this is when the boundary is close to well, the steep increase in the derivative before reaching the 0.5 slope is used to diagnose the boundary in the channel. Okay, so this is how, depending on the derivative curve, you could understand the type of flow and the physical nature around the wellbore. Okay, so this is how when you have a first bounded channel. Now intersecting fault. Same thing here also, the presence of two intersecting no flow boundaries may be felt by the transition from an initial M slope. This is conventional analysis. Okay, so M slope semi-log straight line to a second one with a slope of 2 pi m by theta. Okay, so theta is the radius. So this theta is the intersecting angle between the two fault. Okay, angle between the two intersecting fault. So you could understand, if the well is located closer to one of the boundaries than the other, a straight line with a slope of 2m may come before the transition to the one with the slope of theta only. Okay, so this figure actually corresponding representation of the semi-log graph paper for build up. So this you can say initially you have this slope, then this slope depending on the, this is what you see well, this well located boundary are very near, okay, where this well is far away from both the boundaries, so that's why it is here. And when we are plotting it in our normal semi-log graph, you could understand here the same thing. Okay, so one is closer, so this is, you see, as it is closer it felt the restriction of the flow, that's why it started very early. Okay, this is your normal pressure versus time plot, and this is the semi-log. So it started early, whereas it is flowing 0.5 straight because it is not straight encounter the two intersecting fault. Okay, now this is increasing because now it is coming the effect of your boundary effect. Okay, so this is what is happening in case of, so theta value is not 90 degree here, you mind it, it is not 90 degree, it is just a diagrammatic representation, so it may change theta value. So when the angle is very small, the two faults can be considered as practically parallel. Okay, they behave like a channel. So what we discussed, channel, that means the transition between the stabilization at 0.5 and the one correspond to a quasi-linear flow with the derivative increasing as a half slope straight line. Okay, so you can see here infinite reservoir, we remember that when you have a zero slope, then the first boundary has reached, if the boundary is 90 degree, okay, then if the boundary is 40 degree, so you can see 1 degree. 1 degree means you're going straight, and when you are getting the value of intersecting the two faults, your slope will be changing. So this is how, it's not that always you are getting a pseudo steady boundary, but for different physical reasons, physical barrier, we may also encounter the change in your flow pattern, and in conventional way it would be sometimes giving us some problem, but when we do the derivative plot, the slope of the graph will give us some idea about how things are happening. So it may be due to restriction, it may be due to the physical barrier, or maybe some faults, maybe channels, so that we need to be very much knowledgeable to understand this specific effect. Okay, so this is the same thing, what it's a semi-log plot, you can understand how the slopes are changing, and this is the changing when the well is very close to the boundary, where the well is not close to the boundary. Okay, so now you see angular radial flow, it is more or less same what we discussed earlier. So when you are changing, that means what, when your support system is not let's say edge drive reservoir, what we call the bottom drive water drive or edge water drive. So when you have a edge water, that means in a specific angle your support is there, or maybe when your well is located in here. So by just getting the same theta value, we could understand how the things are changing. So just if you look this graph, it would be very easy. Okay, so you see this is your 170, 270 degree, 170, 140, 120. That means when you are this theta angle is getting smaller and smaller, that means you are getting the steep slope of your graph. Okay, so that means these are some of the important information which help you to understand what is happening into your flow behavior. Okay. Now I told you other important informations also. So this is a well where you have a fracture. Okay, then you have a fracture, then another same thing. So, okay, so now if we just try to analyze a well, how the flow behavior should be, you could understand initially it is linear flow. Only the flow will be through the fractures. But once the fracture is now drained out, because already the matrix is started supporting here. So here in this case bilinear flow. So you could understand when we have fracture around the well and then we allow it to flow, after it, sometimes what the fracture flow is such that it also subdue the effect of a skin if it is there, because you may have a skin around but the fractures is very wide, so flow should be immediately to the well and that can subdue your skin sometimes. Okay, so that means ultimately you have enhanced your flow. So initially you were getting a linear flow, then now you see the bilinear flow. Okay, and what we discussed during our fracture reservoir type, so you have understood there is a transition. Okay, so inter fracture permeability, these are important. So graph shape and graph slope, and the transition zone will vary depending on this fracture permeability and also the matrix permeability. So once it is there, you are getting a bilinear flow. Okay, then you see after your both the things is completed, now it has now this fracture is now reached, the transient has reached or beyond the fracture tip. So what you can see, this is an elliptical flow. This will encounter elliptical flow. Then after sometimes this ellipse will be converted to an pseudo radial flow and then radial flow. So that is what is happening. Once we are testing a well for a specific purpose, we need to understand, being an practicing professional engineer, we need to understand what happened to the well, what are the conditions prevailing in the well. So now based on that we need to analyze our well. It is not very easy, but we must understand what is the philosophy behind specific recording of our pressure and accordingly the analysis part. So geological informations will be very much important if we input, because we know some parameters, some slopes are coming in our normal conventional plot or maybe some derivative plot. But what is the meaning, physical meaning of that slope? Is it due to permeability barrier? Is it due to fault? Is it due to what? So that by other means we need to confirm it, and then we need to properly put our specific flow regime into our programming, or maybe you can say your software. Then you can get the proper analysis. If you are not giving proper information, you may not get the proper analysis for your each and every plot. So it's a very simple part. Once we understand the philosophy, then it would be very easy for us also. Okay, so now just if you just go back again the same part, because what we are trying to understand right from our Wilbur storage effect, then skin effect, then after that we enter into our infinitely acting domain. That may be initial part may be dominated by fracture depending on the well activity we have done earlier. Okay, so that means there also we may encounter certain problems. Okay, so that means where one slope may not be, sometimes one slope, it can change also immediately depending on the near well bore effect. Near well bore effect means if your fractures are very wide, that time it affect. Then we are entering into our normal infinitely acting domain. Okay, infinitely acting domain may be homogeneous. That time we may use our state line formulations to get the our specific pattern of flow. If we have a fault somewhere, if we have a channels, we have the permeability barrier, if we have a fracture, then by understanding the slope of the graph, we could easily visualize what is the physical significance or physical parameters or physical reservoir present when the flow is occurring in a specific time. And that is the main part of the interpretation of the well test data, by with the help of either your different plots, your normal Cartesian plot, or maybe your semi-log plot, or maybe your log-log plot, or maybe a derivative plot. Okay, so that is the main purpose what we are going for it. Okay, so now what I'll just show you few figures or pictures which will help you to understand, or we will just give you some hints here, so that I'll put as an assignment this material and you will complete it. Okay, so now this is what you see, the red color is the boundary and we have the fractured well. So now you could understand what should be the slope of the graph in derivative plot. Okay, so initially what you see right from the beginning, so what initially you will be getting a linear, then you may encounter after some day bilinear plot, because you are reaching a boundary here in every case. Okay, so you are reaching a boundary. So now the same thing. Okay, so now here you are reaching a boundary immediately. Okay, so linear, you see the linear, then your pseudo steady state slope. Okay, so this is what is the how you have to interpret in case of your derivative plot. Okay, so this is now another one. You see there is a difference in this graph and the earlier figure. So now in this case what is happening, initially you are encountering the linear flow. Then once the transient or maybe compressible zone reach beyond it, so you may encounter bilinear. Then once it move away from it, you may encounter an elliptical flow. Okay, then you see this layer will be reaching first rather than this layer. So that means you go back to your boundary when it is reaching the boundary or non ceiling boundary. So how the slope will change, that you can see from your early diagrams, and you could analyze it. Okay, so this is how you need to. So this is what you see: linear, then your 3 by 8 slope, okay, CDO elliptical flow, then we are getting the 2 by 3rd slope, okay, then pseudo steady. So each and every part is going to help you to understand what type of, so linear flow, okay, pseudo steady flow, okay, these are the stimulated data, this is the actual data, the dots, okay. So that means when we are, this is another situations, just try to visualize how well. Okay, so now this boundary will be reached first, then this boundary will come into picture, and this well is very closer to this boundary. Okay, now this would be your assignments for solving how the graph should be. You need to write it down, why it is happening, the slopes, and how the slopes are changing at a specific period, and when it would be maintaining your specific straight line value at 0.5 or maybe 1. Okay, so this is what you need to do. So this is another. What I discussed earlier, the same thing here. One boundary is very close, whereas this boundary are more or less same distance. So you can understand how you have to properly change your slope of the derivative plot, and you could understand. Okay, another part. Now this is interesting. Okay, you see your boundary is away, but you have a fault here. Okay, so now depending on the fault, so initially you will be getting what, spherical flow, or maybe you can say your, okay, not spherical flow, it's depending on, generally you consider it's an homogeneously acting reservoir up to this, then you are encountering a fault very close, but still in this direction it is going. So you see you are getting up to this, you are getting an restriction of the flow, then again you are changing your pattern and you are getting your boundary. Okay, so that part you need to check it, try to analyze with the help of your early studies or early presentations what I have put up. Okay, this is another. Okay, so now you see you are encountering two faults, then you are encountering boundary away from it. So that means you need to draw the picture so that at least you could understand what is happening. So initially round, then you are getting, so what we just now discussed, you see these things, then again you are getting an maybe elliptical flow, this, then ultimately you are getting a your infinitely acting domain with the radial flow. Okay, then again you are encountering this fault, then this boundary, and then this boundary. Okay, it may be same distance what I see from the figure. Next, two wells. Okay, so now the interference part will come into picture. So now you could understand how things will change in this same well. Okay, so now it will initially part with both the wells, then they will flow together with an interference, and then ultimately we are reaching to the boundary and we get the response. So this is what in case of the well testing, another well. Okay, so having a fault here. Now, you just try to understand how the things will be, because one well is going to affect other. You have fracture, so two initial part. Okay, so now you just try to visualize, because we have discussed up to one well. Here we have a two well. Okay, two well, both having the fractures, and how the interference part will take into consideration and understand the flow behavior. And in this case, what is happening? One is maybe active well, another is your observation well. So we may not produce from both. Okay, but if it is there, both are producing, try to visualize it. Okay, so this is what I have given here. This is another 30-degree angle. Okay, so well locations is here. How you try to encounter your flow, initially linear, then you are getting an elliptical flow, then ultimately you encounter this fault, and then you are intersecting fault. So use the formulations, try to understand the behavior of the flow, and then you draw your slope with a logical way. Okay, so that means right from the wellbore to the boundary, how the slope should change, you try to logically build your write-up so that it should be meaningful, and because this sort of things would be given to your examination maybe. Okay, so this is what I want you to know this. Okay, so now constant pressure boundary. Now initially the red color one was not, this was a sealing boundary, or it's a complete boundary, seal boundary, but here it's a constant pressure boundary. Constant pressure boundary means you are getting some, not pressure is fixed, that means you are getting some support here. Okay, so that how constant pressure boundary you could understand. Okay, so this is what, how the slope should not change if you are getting a constant pressure boundary. Okay, so here you see three sides are closed and one side is open. It is getting some support. Okay, so that means your pseudo steady support you are getting. Then another part, the boundary, where is you have a channel here or maybe fault. Okay, so how these things, red means it is a fault, sealing fault, and green means it can allow to flow. Okay, another important part is if you have a 2 permeability. Okay, so K1 permeability up to this, then you have a K2 permeability. That is also similar, take this semi restriction. Okay, so and the same thing, that means initially you may get a restriction or maybe flow, then you are getting some sort of things depending on the K1 greater than K2 and K1 less than K2. You need to design. Here it is given here in K1 K1 K2 less than K1. Okay, below part. Okay, another part, see H1 thickness, then H2 thickness. How this is a fracture if your well is located. Okay, so how the flow would be. Thickness, here well locations. Now you can understand. Now you have a 0.5 at 0.5 log plot, 0.5 positions. What is the meaning of 0.5? What is the meaning of 1? Again 0.5, 1, slope 1. Okay, so at you see it's a log plot, is an x-axis 0.5 and x-axis at 1. Okay, and then when you have a slope, this is also in 0.5. So what are the meanings of this? You need to know it. I may put in the in your assignment, so you complete your assignments and try to solve it so that things will be in your examination. Okay, so here 0.5 again half slope, here 0.5 and 1 slope. So what is the meaning of two different situations in both the cases? Because this is just the reverse of what we discussed earlier. So your graph is given, plot slopes are provided. So what are the possible situations you could interpret from this graph or pressure responses or derivative responses? Okay, so these are another situations. You see 0.5, 1, then another we have a 2 also, then we are getting 1 slope. So this each and everywhere you may get certain what a restriction of flow with time, and it is again stabilizing for some time, then again changing the situation. Okay, so now, so this is another. So this is a synthetic diagram. 1 slope, 1 4, 1 half, 3 8, 2 3 1. What is the meaning of each and every slope in a logarithm log plot, and what is the how you are going to interpret the flow pattern with respect to your Q? Okay, so that is what is the main part of your interpretation. Once you study the diagnostic plot with the conventional plot, hopefully